Welcome to the second video for the secant formula. In this video, we'll determine the equations for the maximum deflection, as well as the equations for the maximum stress due to the eccentricity and the axial loads. The general form for our differential equation is going to be this right here, this trigonometric function with now the eccentricity added. In this case, when we apply our boundary conditions, we're going to apply two of them. We've got that the deflection at 0, well, that had better equal 0. And that's going to mean that C2 has to be equal to the eccentricity, because we've got this term is going to just be 0, and so this term, if it's 1, will be 0. Will give us the 0 that we need in that case. We also are going to have that at L, the deflection has to be equal to 0, and in that case we're going to get some other uglier things for arc C1. So that's going to end up being this tangent function here with the eccentricity on the outside. So that means that overall our new deflected shape equation is going to be equal to the eccentricity times C1, which is the tangent L halves square root P E I times the sine of x times P for E I plus E is already on the outside there, plus the cosine of x times square root of P over E I minus 1 for that right there. So that's quite a bit of function for us to deal with. And the maximum value, so the maximum deflection from this, I guess I should have saved red for this one, huh? Is going to be equal to the eccentricity times the secant of L over 2 times the square root of P over the critical load minus 1, and put some parentheses there. There we go. So that is the secant formula, or that is a secant right there. Those of you who are paying attention to the name of the videos will probably be pumped, because it's the thing, but it's not all of it. So this is a secant formula, but it's not the secant formula. This is our maximum deflection, but there's also going to be we need more than just that, right? We're also going to want to look at the critical load. If we look at the critical load, don't worry, things are going to be no more difficult than they already were, because the critical load is still going to be pi squared times the Young's modulus and the second moment of inertia divided by the effective length squared. Same as it was for the perfectly straight and lacking in any sort of eccentricity columns. So this is the same as it was for the Euler buckling load. Now let's look at the maximum stress. Obviously, for the maximum stress, we can do what we've sort of already done in the past, which is to say that we can look at our two sort of cross sections. So let's say we've got one cross section and it's experiencing axial load. Well, in that case, it's going to have a uniform distribution of stress. Everything very flat. So every single region is going to be experiencing the same, one more, a flat stress block, which I guess we could, let's try to draw a uniform distribution of stress. So but we also have bending moment, and so the bending moment is going to give us triangular distributions of stress. Right, so that's going to look like, well, let's give it some depth. It's going to be sort of high on the extremities, and it's going to be 0 at the center. So we can sum those two things together, and this is for bending. So we've got our axial, let's call that stress, and our bending stress. We can add those together, and the maximum is going to be the maximum that we're going to be experiencing. So we're going to pick one of these is going to be negative, one of these is going to be positive. Right? So we'll just pick the one that's positive and say that that is the maximum, or negative, I guess, in this case, because these are columns. So that's going to give us our maximum stress, which will occur where the bending moment is compressive, because these are columns and they're experiencing compression. We don't really have this issue with tension, because you can't buckle in tension. You can just yield or fracture. So that's going to be P over A times 1. That's for this one. Pretty easy to do for that. Plus the maximum deflection plus our eccentricity of our load, E. So that's going to be, they're going to be in the same direction, times C over R squared. Now, C is the distance from the neutral axis to the furthest fiber that's experiencing it. So it's just, it's basically, we usually call it Y in our moment stress equation, but we can't, because there's Y is already deflection. So gotta call it something else. We're calling it C. So that is our maximum maximum stress equation. Obviously, we can plug in this for y max to get just one equation for that. Don't have a lot of green on the page yet. And that's going to give us P over A times 1. I mean, so far it's all the same. Plus E times C divided by, those are two different letters, eccentricity and the distance from the centroid to the furthest fiber. The radius of gyration squared times the secant of the effective length divided by 2 square root P for E A. Alright. Oh. One more parents there. Okay. So this, which also has a secant, this is also sort of the secant formula. Both of them obviously have secants, and it's indeed the same secant, because it's just this is being plugged into this equation. So that is our maximum stress for a column that is under eccentric loading, because the compression that the column is experiencing is going to exacerbate the deflection that it's experiencing. So I'm not going to make you do proofs of this, but you do need to be able to use it. If you know, I'll provide it, but you got to be able to execute. So know what C and E and R are. Okay, now let's pop into doing some examples with this.